Okay, started the recording, and I'll go back to my presentation and we'll look at the virtual machine later on. But for now, we'll get through a little bit more of the presentation. So actually, just one thing that I forgot to mention when I was talking about doing the literature review, and I mentioned the NASA ADS website. If you can't find a paper, but you see it referenced in another work. So for example, back here, I said that there was maybe this paper in this year that you could find interesting. If you go to the references, you'll see references in this paper. You'll see more details of that. But you can also generally find it just from the name and the year. And you do that by going to this NASA Astrophysics Data System webpage, and you can click on these buttons to search by author or first author or year of publication. And so if we search for McGallagher and year 2012, and this is from the abstract of that paper we were looking at, then it will bring up papers from that year. And this one here, discovery of 5 new pulsars in archival data. That will be the paper that announces the discovery of this pulsar that we're looking at. Okay, so this is a very handy tool for finding papers if you can't find it just by Google searching, for example. Okay, so just to recap, we've gone through how to go about doing a so I'm trying to find where I was. We've gone through how to go about doing a literature review for your given pulsar. We've gone through what the data products in the data set that you're working with are. And we've also gone through some noise and timing model properties of these pulsars. And so now we've opened up the pulsar in Tempo 2 and had a look at the residuals. So we now understand the data that we're working with. Let me just turn off my video to save my internet as well. Okay, so we've viewed, let me go full screen. So we've viewed the times of arrival in Tempo 2 in these residual plots, and we've inspected them as a function of frequency, day of year, and orbital phase. And we tried to find any obvious missing parameters. Now, in the pulsars you're looking at, I don't think there should be anything too obvious because it should be at a decent starting point. But by all means, if you think that something looks funny in the residuals, definitely take note of it. Take note of everything that you're doing because if we eventually publish this work, then of course we'll have a section that describes people's contributions, and so it's good for you to be able to explain what it is exactly that you did, so that first of all it's reproducible, but second of all, yeah, you have a record of what you've done. Okay, so we've looked at our data in Tempo 2. Now we want to actually analyze it in temponest. And so this is the program that we use to fit those noise parameters. So the way we do that, and Aditya briefly went into this as well, is you choose a noise model by choosing a temponest configuration file. So this configuration file is what temponest reads in, and it basically contains some switches to turn various noise terms on and off, and it describes the prior probability distribution that it should sample for those noise parameters. So I have set up in the data package that you have, I've set up some configuration files that will fit for just white noise, so just these measurement uncertainty adjustments. And in fact, white noise is something that we always fit. So that will be present in all of these noise models. But there are also configuration files for red noise, which would model that, low frequency or long time scale variations in the pulsar spin stability. There's a configuration file for dispersion measure variations, and there's a configuration file for these E-core parameters, which is the term that's correlated amongst simultaneous observations. And there's also configuration files that have a combination of these parameters. So maybe there's one that has both red noise and DM variations, and there's one that has everything here, and so on. But the first thing to do is always run just the white noise model. So this is called white.c file. This is the first thing to run because this will be our base model. And after we've run this, we will get a text output like what's shown on the right here. So most of this is showing that temponest is currently taking samples from the posterior probability distribution. And this is describing how that process is going as a function of time. It says this prints out. This is showing that we're taking more and more samples from the posterior distribution. So for example, this says total samples. So up at this point, at this print statement, it had taken just over 2,000 samples, and then it prints again once it's taken 2,360 samples. Okay, but eventually when it finishes, this is the message that you'll be left with. And the important number that you need to note is this ln_ev, which is the natural log of the evidence. So this number, 1299 point whatever and some small uncertainty, this is the evidence for this noise model that you have just calculated. And so the white noise model is the one that you want to run first, and you take note of this number, because when we run additional configuration files, for example, with white noise and red noise, we can use the evidence that comes out from that red noise analysis and use those two numbers as model comparison. And basically, we will find out whether or not there is support from the data for a red noise process or not. Okay, so the way we do this is, first of all, if you're in the directory where we were on the last slide, which was, by the way, you don't have to follow along yet, I'll do a demonstration. So if you're in the directory that we were in, which was the directory for 0921, then first of all, you need to make a directory called results. And this is where all the temponest outputs will end up. And once you've done that, you can run this command. So we're running temponest. So tempo2 minus gr temponest minus f. We give it the par file and this flagged tim file. Then we give it the select file. So again, this is saying to ignore low signal to noise ratio observations. And then this is the important part. We give it this -c file argument, which points to the noise configuration file that we want to use. So in this case, we go back a directory, and then we go into configs, which contains all of these noise models, and we grab white.c file. Okay, and if you run that command, you would get something that looks like this output, and you would take note of the log evidence value. Okay, so the other thing you need to do is also note which fitted parameters are in the par file. So we did this just before in tempo2, but it's important every time you run temponest, just note down somewhere, along with the noise model that you're running and the evidence that comes out, note which parameters were fitted in the par file or by looking at tempo2. So I mentioned after Sam's question that you can open up the par file, and another way to check whether it's fitted is if there's a 1 flag next to the parameter in the par file. So yeah, once the noise analysis is finished, you note the log evidence value at the end, which is this highlighted number. And this is the text output that comes out in the terminal. And I think I already talked about this, but I didn't actually. So the other thing to note in Tempo 2 is the reduced chi-squared value. So after you've done a noise analysis, this reduced chi-squared value becomes important. So from now on, when we look at residuals in Tempo 2, if they have noise parameters in the par file, the reduced chi-squared value is relevant because we need to make sure that it's close to 1. Really, it should be close to 1, otherwise it means something has broken. Okay, and the other thing to note would be any parameters with large uncertainties. And once we have a noise model present, parameters with large uncertainties would indicate that perhaps we're fitting for those parameters when we shouldn't have, because they were confused with some noise term, or perhaps it means that they are just very correlated with the noise. So for example, the spin period and the spin period derivative, or frequency and frequency derivative, they are a straight line and a parabola in the timing residuals. And if you take a power spectrum of that, they look like a red noise process, basically. So they can be correlated with noise processes. So yeah, just to note that from now on, when we look at plots in Tempo 2, you need to note the weighted RMS residual as before, but also the reduced chi-squared value, and look for parameters with large uncertainties. And by large, I mean comparable to the value of the parameter itself. Okay, so this is, Sam has a raised hand.
Yeah, sorry, if I may. So can you go back to your when you show the output of the sampler? Yeah. So is there a rule of thumb as to know whether the sampler has converged or not? Like, I don't know. So you just look at the output of the log likelihood, and that's it, or
yeah,
is there a, like, I don't know, acceptance rate or something like that? I'm not sure.
Yeah, good question. So that's more relevant in algorithms like MCMC, where they basically go on forever until you stop them. They can just keep on sampling until you think you've got enough samples, and so it's sort of up to the user to tune it. But in this nested sampler approach, it has a stopping criterion automatically, which is when the uncertainty in the log evidence gets below a certain value. So if you look at these uncertainties printed out here, they get lower and lower with each iteration, which means that we're approaching a solution. And once they get to a certain value, it means that we've sampled the posterior densely enough that we can integrate it to calculate the evidence. And that's the stopping criterion here. So the only condition for this is that you had enough initial live points. So the live points are the initial samples from the prior volume. So the initial samples across all of your parameters. And basically that just needs to be dense enough to be able to map out this distribution. And actually in these configuration files, I've increased the number of live points for each of these models as more parameters were added. So that should ensure that you always have enough live points, but you could run into an issue if you didn't.
Okay, sure. Thanks.
No worries. Okay, so once that noise model has completed, in this results directory, you will see a new par file. Well, there'll be lots of files in this results directory, but so one of them will be, so in /results, there'll be a file starting with, white dash, But if you run a different noise model, this could be white-red or white-dm. This just corresponds to the noise model that you ran. And then it has the pulsar's name and then .par. So because we've got a new par file, we can run this in tempo2 with the same command as before, tempo2 minus grplk, and then the par file, then the same tim file we had before. And again, we use that select file. So now that you've done this, you want to note the weighted RMS residual. So it's displayed here in tempo2. It's also displayed here at the top of the text output when you scroll up to the parameter table. But as I said a couple of slides ago, one of the other important things you need to note now is this reduced chi-squared value. So this is the chi-squared value divided by the number of degrees of freedom. And here it should always be very close to 1 if you've got a good noise model, because the whole idea of this white noise parameter is to make the reduced chi-squared value 1. So if this isn't close, then something's gone wrong. So you can see here 1.04, then that's close enough. Just as to give you a rough number as a rule of thumb, I would start questioning something more than 10%. So I'd start questioning 1.1 or 0.9, and I'd be very suspicious of 1.2 and 0.8, just as a very rough rule of thumb. Was there someone else with their hand raised?
Yes, Oguchuku also has a question for you, I think.
Yep. You're muted if you're asking a question. Can't hear anything. Okay. Well, if that was a question, maybe you can put it on Slack, and we can get to that later. Okay. So now we're up to step 2, which was model comparison. But how about we go to the VirtualBox and actually run this command first of all? So I'll stop sharing and I'll share my VirtualBox. So open your VirtualBox back up and get to where we were. Hopefully you're seeing that now. So if I Control-C out of tempo2, which is where we were, I type pwd, I can see the directory. So we're in this directory if somehow you're lost or not there anymore. Okay, and in my slides, okay, so slide 18, we want to first make a directory called results. Okay, and then we can copy and paste the temponest command. So again, this is tempo2 minus gr temponest minus f, and this is where you give it the files. So the par file, the underscore flag tim file. Again, we have this select file, which filters out low signal to noise observations. Let's expand this window. And then finally, -c file argument, and we give it a configuration file. Okay, so if we run this, it should go very, very quickly because there's not many observations in this pulsar. Okay, and it's done in a blink of an eye. So your pulsars are going to be take a lot longer than that. The reason why I'm using this pulsar is because it doesn't have many and these demonstrations are fast. Okay, so give everyone a chance to run that command, and you can scroll up as I did in the lecture, and you can see that the output of temponest shows the samples converging on a solution, and then it prints out the log evidence value for this noise model.
And if anyone still wanted to ask a question live, they're very, very welcome to do so.
Yeah. Okay, so I'll assume that everyone was able to run that command. So again, when you do this on your own pulsar, at every time you need to note which parameters were fitted. So we would have noted down that the DM is fitted, which noise model we're running. So we'd note that we're only running the white noise model, and what the log evidence was. So we would note that down in a document somewhere and say, this is what we did. Okay, if everyone could look at the look at my Zoom now, I'll just show you a couple more details about that configuration file. Sorry.
Daniel, maybe we can also suggest as note keeping for people to pipe their histories to files every now and again. It can be confusing, but it can also be helpful.
Yeah, okay, that's a good idea. Whoops, where am I typing? Oh no, I've clicked somewhere and I've started typing. Okay, yeah, so if you just type in history into the terminal, you'll see a collection of the commands that you've typed. And so if you type history and then an arrow to history.txt or something, you'll send that output into this text file, and this will be a good thing to monitor. Okay, so I wanted to just show you some details of this configuration file. So if I open that up in Nano, this white noise configuration file. I think Aditya went through some of these details. The vast majority of this you can ignore, and you can ask me about later, and we might change some of it, but the most important parameters are this root parameter. This describes where the outputs will be saved. So they'll be saved in this results directory. And within that, they'll have the leading term of just white dash, which describes the noise model. So this will be different for the other noise models. Then down here, we have a description of the white noise parameters that we will be fitting. This one means that we're fitting an EFAC, which is just a scale factor to the uncertainties. An E quad means that this is a number that we're fitting in quadrature with the uncertainties. Later on, if we turn on the parameter where the noise is correlated in simultaneous observations, then that will be this parameter here. Okay, and further down we have red noise and dispersion measure variations. So at the moment this is 0 because we're only fitting white noise, but in some of the other configuration files you will see red noise equals some number here, and this number chooses the model that you're fitting. And we'll be using this this third power law model, which is described in this paper, Lentarti et al. 2013. So this is just selecting the model for the power spectrum of red noise and the model for the power spectrum of dispersion measure variations. So further down, we set the prior probability distributions for these parameters. This is probably too technical, but you can look into this later on. And further down, we'll get down to this right at the bottom of this lecture, hopefully. But these are lines that you would uncomment if you wanted to sample the timing model parameters. So Ryan, in Ryan's talk, he described that because the timing model parameters are linear, we can analytically marginalize over them, meaning that we can simply integrate the probability distributions analytically, and we don't need to actually sample them like we do our noise model parameters. But for some highly nonlinear parameters like the Shapiro delay, or some very low signal to noise parameters that might be correlated with your noise processors, it's useful to be able to sample them simultaneously. And so you would do that by uncommenting these lines. The numbers here, 1, 2, 3, 4, they indicate the number of the fitted parameter in the par file. So if you have 5 fitted parameters in the par file and you wanted to sample the 5th one, you would uncomment this line here. Okay, and just down the bottom, these are some properties of the sampler itself. So n live is that number of live points parameter that I was describing before. So as the number of parameters that you're sampling over increases, this n live should also increase. But I've already done that, and yeah, so you shouldn't need to worry about that. Okay, so I'll assume everyone was able to run that temponest command. And now it's time for us to look at it. Did I do this already? I've forgotten. Can someone remind me? Marissa, maybe? Did we already look at the residuals?
No, we've not.
Okay, so we've got the output from temponest. So the relevant command here is on slide 21. Oops. So copy and paste it. This is the command. So again, it's tempo2 minus grplk for the graphics plugin. But now instead of that old par file, which is in the directory we're currently in, we'll go into the results directory and use the par file, which is white-pulsarname.par, and use the tim file and the select file as usual. Okay, and here we are. It won't look too different because the noise model wasn't that complicated, but right at the top of the text output when we run this command, there's this line hidden away, updating TOA errors using TN parameters. And this is just indicating that it's found the noise model parameters and it's now updating them accordingly. And so, as I said before, once you run this, the things to note are the weighted RMS residual. If it happens to be different, or even if it happens to be the same, just note down what it is. And also note that the chi-squared value is close to 1. That means everything's working. And the other thing to do...
So
yep.
Sorry, shall we do a couple of thumbs ups just to see how many people have got that all running?
Yep, sure.
Cool, seeing one. Also feel free, apart from asking questions, to also just ask for extra time to quickly get something sorted out on your end. It would be good to keep as many people on board as possible.
Yeah. Okay, so as I mentioned in my slide 20, the other thing to look out for are parameters with large uncertainties. So here we're only fitting one parameter, there's not really a risk of that. But what you would look for is that this number in the table, this is the uncertainty. So if this number is sort of comparable to the measurement, then it's a cause for concern. If it's larger than the measurement, then it means we shouldn't be fitting for it, basically. Okay, so that was an initial example of what temponest does. I'm just going to CD into the results directory. So if everyone can watch my virtual machine output again, I'll just give you a quick...
Daniel,
yep.
Sorry, I'm not finding good spots to interrupt you. There is a question saying that the last command was missed and asking if we can paste it in the chat. So maybe I'll take on that role to try and copy and paste your commands
Sure.
to the Zoom
the
chat.
one on slide 21 is how to view the par file. Yep. Okay.
So I've posted the tempo2 command that we ran last.
Yeah, okay, so that's the command that brings up the residuals, and yeah, you're just meant to note the reduced chi-squared value, the weighted RMS, and any parameters with large uncertainties. Okay, so I've just gone into the results directory, and I'll type ls to see what's here. ls minus l. Okay, there's a lot here, but I'll describe the important files. First of all, there's the par file, which is what we've been looking at. There's also this .params file, which I will look at. Can I do this? No, I can't. Okay, so this is a list of the fitted parameters, and unsurprisingly, it's not very exciting in this case. We've just got one EFAC and one EQuad. These are the white noise parameters. But this file will become important later on. If you're trying to sample timing model parameters, as I said, by in the configuration file, you uncomment those tempo2 prior lines down the bottom. It can sometimes be confusing whether or not you've uncommented the correct parameter. So when temponest is running, you can check the parameter names that are being sampled, and you'll be able to see if temponest is sampling the parameters that you actually intended. If not, then you uncommented the incorrect line in that file, and you should go back and change it. Okay. The other important file is stats. Let's have a look at that one. So stats.dat. And this will contain the log evidence. There's two different types of the evidence, but for practical purposes, they're the same. You can look at either one. This is, well, note that this is 0.1299, but also at the end here, times 10 to the 4. And so this is the same as what we were seeing in the text output. So 1,299. So this is a record of the log evidence, meaning that if you lose that text output, which was just displayed to the terminal, this is where you get the log evidence again, and if you want to compare multiple parameters. What else? So post equal weights.dat, this contains just a list of the posterior samples. You won't need to look at this, but this is what's used to make a corner plot. So this contains, I think, the parameter values, the EFAC and EQuad, the parameters we're sampling, and then the evidence. And I think the final important one is this T2 scaling.txt. Okay, so in this case, we've only got one parameter, but when you run on your pulsars with many more fitted parameters, and particularly when you're sampling parameters, this will contain numbers that will scale the posterior samples into physical units. So in this case, it's not interesting or exciting, but this will be a very important file later on when we sample timing model parameters. Okay, so that's all I wanted to show. I'll go back to the 0921 directory, and I'll also go back to the lecture. Okay, so we've had a look at the results with our noise model. Now it's time for us to do noise model comparison to figure out what description of the data, what noise model description of the data is best. So the next step is to choose a new noise model. So they all have white noise, but you could choose to fit for red noise, DM variations, or this E-core correlated noise parameter. And you do that simply by running the same temponest command as before with the old par file, not the one in the results folder. Again, the flagged tim file, the select file. So all you're changing is this config file. So you go to the configurations directory, white noise, and in this curly brackets, you replace noise with whatever model that you're wanting to compare. Okay, and then you do the same thing as we just did with the white noise. You run that and you note the log evidence. So I've done that here for 0921. You might get slightly different numbers, especially because I think I changed the data a little bit. But basically you get this, these evidence numbers. So for the red noise, I got 1299.87, DM noise 1299.93, and the correlated noise 1299.67. Now, that might not mean much yet, and that's fine. The way we interpret this is we form a Bayes factor, which is how we do model comparison. And the Bayes factor here, well, the log Bayes factor is the difference between these values. So let's say we wanted to compare white noise only versus white noise and red noise. So the log evidence for white noise only was this. It was 1299.41, and I got that from a previous slide. The log evidence for white noise and red noise is 1299.87. And so you take the difference between these, and the difference is 0.46. And that is your log Bayes factor. Okay, so how do we interpret that? So if this log Bayes factor is model 2 versus model 1, so in this case, model 2 is red noise, model 1 is white noise only. So if this is less than -3, then that means there's negative support for model 2. In other words, there is support for model 1 versus model 2. If it's between -3 and 3, then there's no preference. You can expect this just by statistical chance, basically, or if there's very weak evidence, but it's not important. Greater than 3, this will be our criterion for positive support. So if you run these various noise models on your pulsar and you see a log Bayes factor of more than 3, then you will accept the new noise model. And if it's greater than 10, that means it's strong support, basically. It means you shouldn't have any doubts, pretty much. There are some caveats for that. You have to make sure your data is meaningful, but basically if you get a big number, then that's good news. Okay, and so in this case, if you look at the log Bayes factor, they're never above 3 for this pulsar. They're always in this regime. -3, the log Bayes factor is between -3 and 3. In fact, they're very close to 0, basically. So there's no preference. So there's no preference for red noise or DM noise or correlated noise, meaning that we only have white noise in this data. And we're basically done in this case. In your pulsars, you're likely to have evidence for some of these noise terms. If you have evidence for DM, you could also try fitting for DM1 and DM2 in your par file, and then running this analysis again and seeing if the noise changes. So basically, this DM noise model is just the power spectrum component. So if you have DM variations, it's worth checking whether you also have this linear component. And this is a quadratic component. Basically, these act as a pre-whitening, so they can deal with very, very steep spectrum DM variations.
Daniel and Sam had a question on the Slack channel earlier on. I see he dropped out of Zoom, but he's back now. Would you like to ask your question, Sam?
Yeah. When you show the parameters for the priors of the parameter that you're feeding for, it appears to me that they're all flat, right? Does that mean that for say you're feeding for a white noise, say, so we have a very good understanding about the range of the prior. Does it make sense?
Yeah, the priors are deliberately very broad as to not be too informative. So they're flat, but they're flat over a very wide range. So in this case, we're not using any previous measurements or any initial guesses about what the white noise should be. So yeah, the priors are uniform and broad. Well,
okay.
In fact, for parameters like the red noise amplitude, they're actually uniform in log space because there's many orders of magnitude covered by these parameters.
Okay, just one last question because I also missed this DM1 and DM2. How do you add them again? Can you repeat your last couple of sentences maybe if you don't mind?
Yeah, I didn't actually describe how to add the parameters. I will do that in another slide, but basically, if you open up your PAR file just in a text editor like Nano, you can just type in DM1 and then a space and then the parameter value, which you can just put as 0, and then a space and a 1. So you basically copy the format for the other parameters. So all other parameters are a name, then a value, and then a flag to say whether or not you're fitting. If there's no flag, it means don't fit. But basically, if you want to fit the parameter, you have a 1 in that flag. So to add a parameter like DM1, you would type in DM1 space 0 space 1 in the PAR file. Okay. The other way to do it is just on the command line. So actually, in this tempo2 command, in temponest or in PLK, you can actually type -fit and then DM1, and that will do the same thing. It will assume that the initial parameter value is 0, and then it's going to fit for that. And I have an example of that later on.
Okay, so just one last thing, just to follow up. So if we use the white say -dm.file, it makes more sense to add these two parameters, or?
In most cases, I would say yes, but so these describe a straight line term and a parabolic term. And if you have very weak DM variations in your data, then these may not be significant. And so you're adding parameters to the model that don't really need to be there. So we need to be just a little bit careful about overfitting.
All right, thank you so much.
All right. Someone unmuted. I just muted you. I wasn't sure if that was deliberate. If it was, then feel free to unmute yourself again and ask a question. Okay, so yeah, this is the command to run. Basically, you're just changing the noise file, and it will be saved to the same results directory, but yeah, with a different leading string to differentiate the noise models. And I said this before when I was describing the contents of this results file, but the stats file that's outputted here contains the log evidence in case you lose it. And so once you've run this command for multiple noise models, you can use grep, which is basically searching for text inside a file. So grep for this string, for all of the results in that, all of the stats files in that results directory. And this will give you a summary of the evidence for these various noise models. It's a shortcut, really. Okay, and yeah, this will also answer your question, Sam. So how do we test for additional timing model parameters? So I described in my data analysis lecture, and Ryan also mentioned it, that we can use a test on the chi-squared value in tempo 2. So what we could do is, take our tempo 2 command from a few slides ago, where we were looking at the par file from our noise analysis, so using the par file in the results directory. And if we modify that par file and add some fitted parameters, we can see whether the chi-squared value decreases. So the AIC says that the model makes an improvement for each new parameter added if the chi-squared value decreases by 2 or more. So that's a rough way to go. The problem with that is that the chi-squared value relies very heavily on the uncertainties being correct. And that's an issue here because uncertainty adjustments are part of our noise model. So very weak, weakly significant parameters from this AIC test are likely to be incorrect because they depend too much on the noise model and the uncertainty adjustments. So perhaps a better way to do it is to add these parameters and run it through temponest, which will take into account the new parameter as well as the adjustments to the uncertainty simultaneously. And you can test whether a new timing model is significant, a new timing model parameter is significant in the same way as we were testing the noise models before. That is, you add a new parameter to the par file, or you do it on the command line, which I mentioned before and I'm demonstrating here in this example. And then you see what happens to the evidence. And it's the same criterion. If the evidence increases by 3 or more, then there is support for that new parameter. Okay, so I've just done an example here for this pulsar 0921. So the way I would recommend doing this, what did I say? Okay, yeah, so this becomes a little bit tricky because if there are already results in the results file, if you try to run a new temponest command, it will see that those results exist and it will say, oh, great, I don't need to do any sampling, and it will just print out text and not actually do anything. On the other hand, you may not want to actually delete the results that have already been done, right? So if you want to test whether new noise model, new timing model parameters are significant, what I would recommend you do is remember to change the root file name in the configuration file. So this again is where the output is going to be sent. So to do that, whatever noise model you think is best, so in this case, it was simply the white noise model, but you may have landed on a different noise model as your best noise model. Whichever one is best and you want to use for this testing purposes, copy that to another file. So just add an underscore test in the file name. And then open up that test file and change the root output to results underscore test, right? And then I didn't write it in here, but of course you also need to make a directory called results underscore test. And that's where this new output will go. So once you've done this and wherever you're keeping track of what you're doing, note that you're trying a new parameter. So let's say, note that I'm adding px, which is parallax to the par file, or I'm adding -fit px to the end of my command. This is probably the easier way to do it. So maybe ignore the par file. Let's just stick to doing it on the command line. Okay, and once you've done that, so in this case here, so I would have created a configs, there should be a slash here. I'll edit this in a second. So this is the temponest command. Again, the old par file, not the one with the noise parameters, the flags, tim file, the select file, and the configuration file. So this is configs, it should be slash white_test. So this would be the file that I've modified to change where the output goes. And then at the end, I write fit px. And then this will be fitting the parallax, or marginalizing over the parallax. Remember, integrating over the probability distribution. And then fitting for the noise models. And the result of that is here. So the log evidence in this case is 12.89. So it's actually decreased by 10. And this indicates that we're overfitting. And we're overfitting in this case because there's only 8 observations. So it's not too surprising that the evidence goes down, because you can't fit many parameters if you only have 8 unique epochs. This is likely not to be the case in the other pulsars that you analyze. You might find some parameters have positive evidence, and if so, definitely note those. That would be exciting. So the reason why we created this test directory is that after you've done that, so that you don't need to create a new directory all the time, you can delete the contents of this results.test, and then you can change the parameter here and try something else. So for example, if we try FD1, so just replace this PX with FD1, and you would get another evidence, and again, it's lower. And you could do the same thing for other parameters. So for example, the proper motions. And for proper motion, you actually need to fit for both proper motion in RA and declination. You can't just fit for one component. So here you would just write fit PMRA -fit PMDEC to fit both of them. And we've added yet another parameter, and the evidence has gone down even further by about another 10. So this is definitely no support. So for this pulsar, if you were to repeat this process, basically there's no evidence that you should be fitting for any of the other parameters. And the reason for that is that the initial par file is already pretty good. So the best description is using the numbers that are already in the par file, and then just a simple white noise model. And that is essentially the end of the story for this pulsar. And it's very boring, which is why you're not going to be analyzing it on your own. Okay, so I've almost been speaking for another hour already. Let me just quickly see what I have left. Maybe we'll do another demonstration and then have a break.
How about a quick break and then a demonstration?
Yeah,
5-minute break.
Sounds good. I think actually we're getting close to the end of what I wanted to show for today. Anyway, a lot of the other material we can revisit when we keep in communication, but these temponest analyses could take a while to converge on a correct solution. And if you finish one pulsar, then you can move on and work on another one. So yeah, we'll have a break, say 15 minutes. So we'll meet on the hour, 17 minutes.
That sounds great. Thanks.
All right. So see you all on the hour.